Good afternoon, everyone. My name is Juan Mateus Sanchez. I am a technology researcher from the National Institute of Metrology, Quality and Technology from Brazil, Inmetro. And today I'm going to present this paper called Development on an Upgraded Efield Strength Probe to be used as a transfer standard for metrological purposes. The authors of these papers are Dr. Donglin Meng, a researcher from the National Institute of Metrology of China, and me. Okay, let's go to start with the following question. What Efield strength is? Efield means electric field. The sensor probe developed in this work is to measure the electric field component of electromagnetic fields used in a variety of radiofrequency applications. From navigation communication, AM, FM, radio and TV broadcasting, to mobile communication and satellite communication, all this application needs to measure the electromagnetic fields generated by the antennas used to transmit the signals. All those measurements need to be done by instruments which need to be calibrated periodically in proper calibration facilities to warrant proper accuracy. As mentioned, in general, Efield strength needs to be measured in many ways, and the accuracy of such measurements is granted through calibration facilities. Calibration facilities are devices which generate a reference Efield strength against which we can compare the reading of the instrument making that measurement. As an example, transversal electromagnetic cells, called TEM cells, can generate this electromagnetic field strength. There are also testing facilities used to verify if electronic devices are susceptible to electromagnetic fields present in the environment where they are installed. This is the immunity test facilities. An example of this is the Inmetro G-TEM Cell. The NIM TEM Cell goes from 10 MHz to 1 GHz is another example. Sensor probes are used in semi-anechoic or anechoic chambers to verify the uniformity of electromagnetic fields generated during immunity test. All these measurements need to have the proper traceability to the primary reference standards. How to bring traceability? In Brazil, we have no reference standard for radiofrequency quantities. Because of this, we make a cooperation project with the National Institute of Metrology of China. In these pictures, we can see the NIM's primary standard for Efield strength. It is composed by this signal generator from 10 MHz to 1 GHz, the primary standard that is a micro TEM cell, this device here, and also a power meter, that is this device. In addition, we have the transfer standard, that is this device here. Basically, it is a sensor probe that is called TFS11. Once the TFS11 is calibrated in the TEM cell, the readings are recorded, and the sensor can be used to measure other generator facilities, allowing to obtain what is the error regarding the micro TEM cell, that is the reference standard. This paper presents the development of a sensor probe to be a new transfer standard to substitute the current one, which is not manufactured anymore. The specific goals of the project was to improve the uncertainty, currently less than 1.5 dB for Efield strength, keep a broadband frequency range at least from 10 MHz to 1 GHz, to keep the small size or to minimize or avoid disturbing the field uniformity, to improve the usability during the measurements, and to have a backup in case of damage of the current probe. In this picture, you can see the hole through we pass the transfer standard that have a diameter less than 10 millimeters. The first thing that we did was to study the key factors for Efield probe design. The theory was presented in many papers from Dr. Matsuhide Kanda between 1985 to 1990, and basically a sensor probe is composed for a dipole antenna that was sensed by the diode bonding paths. This diode is a Schottky diode that defines the low limit of frequency range. The dipole antenna also defines the high limit of the frequency range and improve the sensitivity. And the high impedance resistance lines after the diode creates a low pass distributed filter helping to match the signal. With this in mind, we started to design the desired features for our prototype. First, the size restriction that the sensor probe head needs, so we specified the dimension of the sensor needs. Secondly, the small electro-optical conversion, and also a new reading software to deliver the measurement directly in a laptop. Because the selection of the electronic components is besides our experience, we contact a Chinese company called STT that is have more experience selecting the components with these specifications. In this picture, I would like to show some sensor head evolution. So this is the first prototype that we presented. After that, we make this other, and also make some modification in the design of the electro-optical converter, and finally we make some modification in the optical receiver to conduct the signal to the laptop. Well, this is the final prototype that received the name of FTTRF06M. So in this picture we can see the new Efield probe being calibrated at the NIM's primary standard. The next steps with the new prototype was to carry out performance tests. So the first thing that we did was to determine the dynamic range and the frequency response, but the point of view of accuracy. So the dynamic range is the ratio between the minimum and maximum Efield strength that the sensor can measure. The STT declares that the dynamic range is 50 dB, but how to verify this data? So exploring this dynamic range, we discovered that we need to formulate a new dynamic range definition. In this work, we consider dynamic range as the difference between the largest and smallest values that the sensor probe can measure accurately. So in the equation that we formulate for dynamic range, we include the error at the highest and the lowest Efield strength. Then we obtain the sensor probe error versus the frequency range. So from 3 volts per meter to 70 volts per meter. So applying this definition, we can obtain the dynamic ranges. The main findings that we obtain is that as the errors at 1 volt per meter are too large, correction factors are not reliable. So the traceable reliable Efield strength range is from 3 volts per meter to 70 volts per meter. This slide shows the results to exploring the frequency range. In these limits from 10 MHz to 1 GHz, the STT sensor attains very well the project goals, but we trace the dynamic range between 500 kHz to 2.1 GHz. So we discovered that the dynamic range is pretty close the same. So we conclude that the STT sensor can be used in this frequency range, which is a greater advantage over the old TFS-11. Regarding linearity, we can see in this plot the reference Efield strength from 0 to 25 volts per meter versus the STT Efield reading in this axis. So we plot the linearity from 500 kHz to 2 GHz. So In each frequency, you can see that linearity is kept in this frequency range. Another performance test is selectivity. In fact, because the Efield sensor probe just measures in one direction, selectivity is the capacity of the Efield probe to reject orthogonal components of the Efield. Selectivity was obtained from measurements in the TEM cell. Selectivity values was computed by the following equation. This figure shows the Efield reading against the position of the sensor probe when it is rotated inside the TEM cell. Observe that the position in 90 degrees produces the highest Efield reading. It shows also that the readings are proportional to the sine function of this rotation angle. So this figure also shows that, a conclusion of this work is that any misalignment can produce very few effects in accuracy. To evaluate repeatability, we record more than 31,000 readings of a constant Efield strength of 20 volts per meter in one day. All the readings were plotted in this figure. The readings were taken in one single day from 10:30 a.m. to 4:30 p.m. The results of these 31,000 readings produce an Efield reading average of 19.96 volts per meter with a standard deviation of 0.02 volts per meter. In order to evaluate the stability of the STT probe over the time, we take measurements in 3 different days among 5 weeks. This table presents the results of SAC measurements and show a small drift of 0.66 volts per meter in 5 weeks. After the performance test, it's time to talk a little bit about the uncertainty evaluation. NIM computes the reference Efield strength through this equation. This equation is the basis of any TEM cell, where the main variables are the input impedance, the power reading, and the length of the septum, that is this distance here. NIM apply specific correction factors to these variables that are applicable to its own system. The measurement uncertainty equation is given here with the sensitivity coefficients. Basically, after making of the computation, NIMs conclude that the uncertainty of the generated Efield strength is estimated in 0.44 volts per meter. For the transfer standard, the mathematical model is given by the following equation. This is the transfer standard reading, this is the reference Efield strength, and this is a correction factor due to repeatability, and this is a correction factor due to misalignment of the sensor probe inside the TEM cell. The combined standard uncertainty is given by this equation. The estimation of this uncertainty is estimated from repeatability test. This is the estimation from selectivity test, and finally, this is the estimation from the uncertainty of the reference Efield strength that was estimated in previous slide. At the end, the combined standard uncertainty gives 0.45 volts per meter. Finally, during this project, we have taken the following conclusions. A transfer standard sensor was developed and tested in the frequency range of 500 kHz to 2.1 GHz from 2 volts per meter to 70 volts per meter. A new definition of dynamic range in terms of accuracy was introduced, making more sense from the metrology point of view. The rejection of cross-polarization components was also tested, showing reasonable performance. The repeatability was also evaluated, showing that uncertainty is less than 0.0 dBs and stability tests show a low drift over the time. We conclude that the new Efield strength sense transfer standard is suitable to be used in future key comparisons. So thank you very much for your attention, and I am open for questions.